Hi, hello everyone. I'm Mitsuhiro Kamilaki from Western University, Japan, who is one of the organizers these workshops. So let me introduce briefly the next speakers. Next speaker is Lik-Hang Lee. He's an associate professor with Korea Advanced Institute of Science and Technology, KAIST, South Korea, and he leads the Augmented Reality Media Laboratory, KAIST, and he received the PhD degree from SyMLab, Hong Kong University of Science and Technology, and the Bachelor's and a Master of Psychology, Philosophy, degrees of freedom. Degrees from the University of Hong Kong. He has built and designed various human-centric computing technology, specializing in augmented virtual reality, AR/VR. Okay, Professor, please give us talk.
Okay, hello everyone. Can you see the screen? Building user-centric immersive city in the Metaverse. Okay. Yeah. Okay, so I think in this talk we already, I think other speakers already mentioned what is XR. So I won't spend much time to describe this, but I would like to emphasize that Metaverse consists of many types of virtual environments, like augmented reality, virtual reality, or in between we have the augmented virtual reality. This build up the very large spectrum of the extended reality. What is the opportunities in the Metaverse? So here is the idea. So if we want to build up the Metaverse, actually we need to experience three phases. First, we need to copy our physical world and therefore make digital twins. I actually come from Hong Kong, so this is Hong Kong Victoria Harbour, and so we build up a digital twins version, and I think it is mainly virtual reality. And then we invite people to work on the content, and a lot of users engage in such a digital twins. If we get some very meaningful or useful contents in the digital twins, then we can bring it back to our physical world. So this is the final stage, like a virtual physical blended environment. So what we call is Metaverse. It is more relevant to AR or augmented virtual reality. To build up the Metaverse city, actually we need to consider 3A principle. Okay, so this 3A principle try to address the user interaction with city-wide immersive applications. First, add on highly mobile scenario, the user will interact with the city-wide AR applications in outdoor. And second, accompany with other IoT device, and AR can leverage the capabilities of IoT device in the smart city. And third, we also need to make sure all the users having their privacy and safety requirements. Right, so I will go through them one by one according to the 3 principle. So I will give some example what I have been done in the past several years. And the first is like user interactivity. That means we need to improve the user input and output channels with AR and VR. And for input here, you can see that input solution enable users to convert their intention into action in virtual environments. However, it is very challenging. Here is a video on the Google Glass. You can see that the user use the swipe gesture. Actually, it is inconvenience and also make some burden with the user interface. So here, if we want to type SyMLab, SyMLab, but the voice recognizer can only make seamless. Okay, so and what about we have a joystick on the smart glasses? So the user try to type SyMLab again on the web browser. But you need to turn your finger 16 times faster here. Okay, so it seems it is very inconvenient. So that's why we have to describe. Okay, we need to consider all the mobile input solutions here. So one of the design consideration is the user mobility in the city. So for example, we try to keep all the character input in one hand, as shown in this device, because we want to keep another hand for other physical tasks or other tasks in the AR or VR. But we also need to consider other situations when we have no free hand. So we may employ some sensor like this EMG sensor with the advanced deep learning method here. So the user can move their arm even they are holding a pen. As shown here, here is a umbrella. Holding umbrella, then the user can still do the interaction in the virtual environment. And meanwhile, we also need to consider how we can modify the objects easily. For example, in a mobile scenario, our head keep moving. Okay, how we can adjust the head movement to fit for the user movement in an accurate and easy to use manner. That is very challenging. And here is the feedback. Okay, apart from the input, we also need to design the feedback to increase the level of realism. So, but what we can see in the HoloLens, okay, we only see the part of the image. So that means we have very limited field of view. So, but it also restricts how we design our keyboard. For example, in the conventional keyboard, if you put this keyboard in the middle of this inside the screen, actually it become a hurdle between the user and the physical environment. That's why we design some keyboards trying to minimize the keyboard size and make it invisible. So the user here, based on the alphabetic order from A to C here, can grab the characters the user needs. And then finally, the user can make the output research, okay, here based on our probabilistic approach to advise the word. And due to the limited field of view, we have to select and organize the visual content wisely. I also have a series of work to demonstrate the content management on AR smart glasses, AR headset, and AR windshield on smart vehicle. So on the left-hand side is the AR smartphone, and the middle is AR headset, and also the AR vehicle. And the key idea here is the context awareness. That is the user interest. For instance, on the left-hand side here, we only show the dim sum menu. Dim sum is a Cantonese food in Hong Kong. Okay, we usually eat dim sum at noon, but not the hot pot. Okay, for the lunch. To improve the realism, we also need to consider the integration of haptic feedback in 3D virtual world. As shown in the right-hand side, we offer some design guidelines for AR and VR developers to decide about the selection of visual and haptic feedbacks. And furthermore, we may want to add wages to improve the realism and object present in virtual environments. And electricity motor here can draw the liquids for adding weight. And in our research, we employ liquid metal, and we compare this performance with water, okay? And then metal liquid shows a better performance for the realism and object present. And after we discuss the mobile input solutions in outdoor, we already know that it is not very easy, and we have a lot of constraints. But what we can do with the human drones interaction or with other IoT device is still a very big empty gap in this area. So we can imagine that IoT device, IoT device is growing every year, and drone is one of the remarkable example. So here I will discuss one work regarding the human drone interactions with the flying drones. I mean, so why we need that? Because like flying drones can borrow the view to the AR user, but it is still a challenging task to design such user interactivities. So the smart glasses manufacturer told the user to put these external controllers of the smart glasses, this one, on the top of these bulky controllers for the drone flight. So we question the way to get rid of bulky controllers and the situation of having multiple dedicated controllers. You know, if we have 10 IoT devices, it is impossible to bring 10 controllers, right? So why don't we consider the strategy employing, putting everything back, I mean, all the resources on our body. So that's why we keep designing some input strategy driven by the user body. Okay, what we call is like body-based interaction. Yeah, but designing this is very difficult. The flights can move in 4 directional movement: longitudinal, vertical, lateral, and rotational. And each movement has opposite direction. And the reach command give justification for 2-hand operations because it is counterintuitive to squeeze all the operation in a touch-based button. So therefore, we are interested in designing a body-centric minimum interface and investigating the input models for flight control. And subtle interaction is preferred because it is awkward to do a full body movement for controlling the drones in a public area with AR. So you can imagine if I want to control drones, but the gesture, I mean the full body gesture is like I need to dance in the middle of the city, and people and the bystander, I mean other people in the city will look at you. So you may give some disturbance to the society. So we need to make it subtle. That is the main goal. So we consider 3 types of input model to shrunken the size of the device, which are touch-based, IMU-driven, more accurately is gyroscope, okay, and force-assisted interaction. Force-assisted, it means we exert the force on the screen, okay. And for IMU movement, we cannot employ the yaw movement because it will conflict with the user walking posture. And for the force-assisted input, we cannot divide this force-based input into multiple levels because it will become erroneous. So basically, we only consider 2 levels. So accordingly, based on the input models, we developed 3 types of gesture: thumb touch and swipe, wrist rotation based on the gyroscope, and force touch. Then we carefully consider this combination to make the interaction happen. So we have 4 candidate solutions and implement them on the smartphones. Then M1 is the unit model, which is the baseline for the that emulating the physical controllers. So we have 2 buttons on the smartphone. You may wonder why we first work on the smartphone, because later on we will make a ring form device. But before that, we take a systematic evaluation to understand the performance first, instead of spending a lot of resources on the ring form device, making the ring form device, I mean. Yeah, so the second one is the M2. Here is the touch-based model with the wrist movement, okay? And M3 is the tri-model, touch, it includes touch, wrist rotation, and also force touch. And the final one is a comparable case with the M3, with the wrist rotation and the force touch. So let me introduce them one by one. This is the baseline, so I skip this. For the touch-based interaction in M2 and M3, we use the thumb swipe for longitudinal and lateral movement. But we need a mode switch here. So the mode switch can switch the mode to the second level here is the idea. So for the second level of M2, wrist orientation indicates the directional movement, and the degree of wrist movement control the drone speed. And for the second level of M3, the wrist orientation only indicates the directional movement, but the drone speed is controlled by the level of exerted force. And for the M4, we basically employ the design as the second level of M3, force and wrist. However, the wrist angle is divided by extremes that indicate the 4 directional movements and their opposite directions. Yeah. So then we run a pilot test with 12 participants, and each participant perform 5 unit tasks, going up, down, left rotate, right rotate, and left and right rotate. with 3 repetitions. So we measure the completion time, wrist movement, interaction footprints, user workload. So yeah, so I cannot go through all the details, but we can see M3 is a better solution, and also it maintains a very subtle gesture, and M3 can maintain a very small interaction area. It fits the ring-formed device. Okay, so M4 got complained by the user. They say that it is counterintuitive, so we will not consider that. But the first task is quite simple. It is some unit task. So we want to retest all the things with a more complicated task. So we recruit another 20 participants, and they need to do a more complicated task, 8-figure route with 3 repetitions. We see that M1, the interaction area just grow to a very large area, but you can see M3 still maintain a very small area as shown in the pilot study. And according to the user workload, M3 is still a very good solution. So who is the winner? So to interact with the drones, we finally select M3 as the winning strategy. Then based on this, we build up a ring-formed device. So the user maintain a very subtle gesture. Basically, you can put this ring-formed device inside the pocket. Then you can control the drones to do a lot of things. But now we move the things from the smartphone to the ring-formed device. So we need to evaluate the form factor. We can see that even we move the things for the ring-formed device, it also maintain the even faster performance, and also maintain a subtle gesture, and also people accept the technology. So you can see we can use it for many cases. For example, we can use the drones to go to somewhere as a physical telepresence, or we can use the drones if there is a pico projector on that. Then we can share the view with other bystander without the AR headset. So many applications we can do together. And the latest work I just published this year is we try to understand what is the performance with the ring-formed device with the drones. So we do something like crossing operation and pointing operations with various environments in the simulator. So then I think later on we can leverage more on the virtual environment to understand how we can design the ring-formed device. Yeah. And finally, I briefly go through the user privacy for safety. As I just mentioned, the 3A principle. So you may imagine someone may look at this. If we try to visualize everything, okay. So actually, it is very dangerous. Maybe people can look at what you are talking about. Maybe someone using the drones can look at this visualized image. So we need to consider how we can stop such privacy leakage. Maybe we can consider the data sensitivity and who is the recipient. So we have some example. For example, good morning is not insensitive. So insensitive. So it's not sensitive. So we need to we may just go with everyone. But if we talk about something like, oh, I got some COVID, okay, then maybe I don't want to share this except someone except who is working in who is my medical doctor, okay. And also I consider mobile scenario in the city for authentications. But in the future, we also need to consider the mobile scenario with the robots. And one of the key challenges is designing the interaction solutions or techniques with low method or software interface like the XR or with the robots actually is quite challenging. And we can see the input bandwidth, there is a big gap. If we use the keyboard or voice recognizer, it is very fast. But if we try to make something like ring-formed device or other new types of interface, you can see the throughput rate here is very low. So we still need to spend a lot of effort to make this happen. So I will stop here. I think I already overrun. Yeah, thank you very much.
Thank you very much, professors. So other invite some questions from. Please. Here's my.
Hello, I'm Monella Chessa from Italy. I have just a curiosity about the interface that you presented about for flying drones. I'm curious to know how much time people need to learn how to use the different new interfaces. So if it is straightforward or if they need some time and how much time to learn how to use them.
Oh, I think the interface, we conduct the test. Usually, the user have no experience, so they just go into our experimental setup, and then they can just try to learn it and improve the performance with multiple sessions. So we can say that it is easy to use. So it seems that we only show a solution and then we publish it, but actually behind that we have many failed cases with a lot of iterations, and finally we come up with very reasonable solutions. So it should be a easy to learn solutions. Yeah, thank you for your question.
Thank you very much.
Thank you. Any questions? Okay. All right. Thank you, Professor Lee. Let's move on to next speaker. Thank you.
Thank you.